I am going to talk to you this evening about combinatorial epidemiology. Under assumptions of perfect or, approximately perfect information, under which assumption we can deduce a conclusion of optimal safety. So, yeah. In epidemics, in an epidemic, and in epidemiology, we study spread. We study spread of illness. We are able to identify two types of spread. There's a spread due to proximity and a spread due to movement. So from this perspective, the measures of blockage or quarantine may be justified. However, the quarantining questions, or the block, as I call it, must be placed optimally. And paralyzing activity is not, in my opinion, paralyzing total activity in a region, in a fairly large geographical region, such as the continent of Australia, may not be, in my opinion, an optimal solution. Spread due to proximity, spread due to movement. By applying generalized quarantine or a block, we are able to reduce the spread due to movement in a particular epidemic. Okay. Now, what I'm going to tell you here does not apply to COVID, because COVID is a non-standard epidemic, if I'm able to call COVID an epidemic. So I will leave that open. I'm going to leave this conclusion to yourselves, the viewers, whether COVID is or isn't a classical epidemic scenario. So I'm not going to address that issue here. In my opinion, COVID is not a classical epidemic scenario, but I'm not going to discuss that. COVID is not even an epidemic, according to my belief. All right. Now, just running quickly over some older slides that you are able to find on my webpage. So I'm going to talk about spread due to proximity, spread due to movement, and the relationship between time of movement and time of detection. And at the end, I will speak to you really quickly about game theory and some new stuff that I did manage to come up with regarding game theoretical analysis on a particular ecosystem. So it relates to the science of ecology in particular. Okay. So let's talk about proximity spread. Proximity spread is described by a unit this graph. Immunization can be done on a vertex cover or any structure describing centrality. There exists opportunity to apply optimization techniques to approximate vertex cover. Immunization of the vertex cover ensures no illness spread is present due to proximity. So, in theory, if one immunizes a population optimally, they will be able to minimize the spread, assuming, of course, the epidemic at hand is an epidemic. That is the first assumption, and assuming it is following the laws of epidemiology described, for example, by Bernoulli and many others after him. Okay, so we are able to operate on unit disk graphs. Unit disk graphs are particular types of structures in computer science. So and they are reasonably well known. So that should not be an issue in this discussion. So using unit disk graphs, we can analyze. Using unit disk graphs, we can analyze spreads due to proximity and apply vertex cover techniques. And by immunizing population optimally, we can obtain results. If we're talking about, if we are talking ideally in this particular case, I must say this. Ideally, in this particular case, a universal vaccine would be something desirable. It would be something fantastic, really, and it is something I'm looking forward towards in the short future. I hope a universal vaccine. Okay. This is computer science. Mathematics is computerized these days. We can use database queries, hard-coded procedures in your favorite programming language. Animal or population movements can be seen as a temporal graph, in which temporal paths are passed through the underlying graph that respect the natural order of time. So we can use techniques from network epidemics, network epidemiology, and temporal graph epidemiology, an area which has been developed in the last 10 to 15 years or so. Okay, as usual we assume an illness, a conventional illness. Yes, a conventional illness that has periods of acquisition, incubation, latency, communicability, and termination. So these are the 5 particular stages in a classical epidemic. And we have to remember an epidemic is bell-shaped, right? So an epidemic follows the laws of natural distribution in statistics. So yes, that's about it on this topic. Okay, so we are able to identify a temporal radius. The spread acts on the temporal network, on the underlying temporal network, and the model that we are able to program easily on a very, very rudimentary conventional machine. Okay, as I said, there's periods of incubation, latency, infection, and termination of the illness in question. There's a problem, there's an all possible paths problem formed that's formed on a fixed radius, the radius of infection, function of the length of latency, and the radius of detection of the length of incubation. The resulting search can be done efficiently because we're talking fixed parameter tractability for a problem that is NP-hard, however it is FPT for parameter length of path, where incubation and latency allow an efficient search, as I said. So this is a rather neat result, and I trust it can be seen immediately. Um, we can talk about we could be able to talk about interesting theoretical problems. Yes, these problems are theoretical, granted, such as patient zero and the relativized, something that I call relativized patient zero. The goal is to compute a complete history of spread and trace the complete paths of illness spread from an infected node to its sources. So we can perform searches backward on a temporal graph by making use of the incubation time radius and possibly latency as well. Yeah, that is the figure there. I believe the details may become apparent to anybody after a careful study of this figure. Okay, classical detection in epidemiology is a well understood technique and a well understood algorithm. It's possible infected location. Okay, detecting infected location is very straightforward. Yeah. So the algorithm is the algorithm in question is detailed nicely on my webpage, on some of my notes that I've compiled on this project. So I hope you will enjoy studying this. In case you are interested, in case the problem of tackling conventional epidemiology, conventional epidemics is of interest to anybody at this point in time. Okay, so time, we can talk about time. Time has direction. We observe discrete periods between trade. Locations are allowed to trade on certain moments in time called rounds. So when I say locations are allowed to trade, I'm saying basically units are allowed to move between locations. So yes, I raised the problem just a few minutes ago. I said a block or a region quarantine must be placed optimally. So I think this is a key point. For example, paralyzing, and I'm going to repeat myself here. Paralyzing entire activity, it's not only not optimal, it's also dangerous. So we get into situations where people are quarantined at home, not able to engage in work activities. They are quarantined at home and they may be in danger, or we can imagine this type of scenario. So I really don't believe a total freeze of activity to be optimal, and I would advise 100%. I'm 110% on this. Paralyzing activity completely is not only unoptimal, it's also very dangerous to human lives in general. Okay, so the interval between rounds of spread, which is network specific, and the interval of detecting the infection, which is illness specific. This is what I'm going to talk about very, very briefly in what follows. Okay, so what happens if so there are several cases here. What happens if the detection radius is 2 times the interval between rounds? So detection equals 2 times r, where r is the length of a round. We observe a block. So this is not an optimal case. We observe a block relatively at a relatively long time after the detection period, which is as I said, 2 times the length of the interval between rounds. Okay, so there are 3 cases here. Detection interval equals round interval, detection interval is more than the round interval, and detection interval is greater than the round interval. If detection period is equal to the round if detection period is equal to the round period, no other spread with this source shall occur after 2 rounds. So this is close to optimal. This is optimal in fact. So detection equals round period. I like this a lot. I like this result a lot, and very neat and very simple. If detection period is less than the round period, no other spread with this source shall occur after 2 rounds. Again, an optimal an optimality result. I like this a lot. And if detection period is greater than the round period, no other spread with this source shall occur after 3 rounds. So this is the case that must be avoided. This is the case. That leads into problems. So yes, that's about it on these very neat optimality results. So that was combinatorial epidemiology under the assumption of perfect information, or something that's approximately perfect information. We can deduce an optimality in safety. So everybody is safe, everybody is happy, people can live happy lives. And I like it's a desirable. It is a desirable result in science in general. So since I'm at it, since we're talking about this, let's talk a little bit about game theory. It's still connected to what I said before. It's perfect information. It's under the umbrella of approximating something that we call perfect information in order to derive optimal safety. There's some notes that I wrote, and they relate to ecology and ecosystems. So it's something that I've done. It's brand new research, something that I've done lately, and I enjoy what I came up with in this particular thing. So we're talking about a binary ecosystem. Keywords are computational game theory, user-defined data structure, and algorithms on user-defined data structures. So we can define user-defined data structures. Sorry for the apologies for the pleonasm here. So we can define user-defined data structure, and once we have these data structures, which are not hard to define, again, I could do it myself in half a day or so. We can run very neat algorithms on these user-defined data structures. So again, a very neat result. It's nice. It's nice in under a situation of quarantine when everything is quiet. It's very nice to sit at home and do mathematics. I enjoy my time at home these days. So we consider a game in which 3 types of players interact, of 2 genders each. A different version of this game allows gender diversity with a spectrum of gender strength of 0 to 1 on each player, where 0 is absolute weakness and 1 is absolute strength. Player A, we can call player A an insect. We can call player B non-insect, or animal, or human, or whatever. And we can call player C neither insect or non-insect. We can call player C a chrysalis. Okay, so there's 2 things I want to talk to you about here. The first thing is animal communication, and the second thing is animal behavior. So let's talk about animal communication. We are talking about a public language, L, with associated set of intended meanings, M, for each morpheme in this language. Private language, P, for which intended meaning is redundant. So yes, we're assuming some people have private language capability. Okay, so under chrysalis communication, there's a basic language. The intended meanings are rudimentary. Human communication is a semi-basic language, unfortunately. The intended meanings are sometimes ambivalent, but very rarely, so this is how we humans communicate. And the insect communication is a complex language. The intended meanings are almost always ambivalent. This is because they have private language capability. Insects have private language capability, which is two-way, insect to insect, and one-way, human to insect. Again, insects have private language capability, two-way, insect to insect, and one-way, human to insect. Now, studying animal behavior, there's a radius of communication, trivial radius of communications for public languages, possibly variable radius of communications for private languages, in any case much larger than the trivial radius. Okay, we can define something called fornication, which is energy exchange, insect to insect and human to insect, and so on and so forth. Various fornication and communication combinations, such as signal interference, generated anxiety, thought insertion, and so on and so forth. And the questions we are able to ask, well, the most important question that I think we are able to ask is the question of detection. Are we able to tell an agent is human or insect strictly from behavior? So we must analyze this carefully. I mean, as humans, we do not have private language capability, so an insect has the upper hand on this particular scenario. So yes, we need to use very smart computational techniques in order to detect, if possible. And I think it should be possible. We must use very smart, very intelligent, very creative computational techniques to detect the fact that an agent is human or insect strictly from behavior. We can ask unwired phone type of questions, such as questions relating to relays, acuity, as opposed to something very strong as an SOS alarm, which is basically something that gets the insects in panic. And an SOS alarm gets insects in panic. We can ask entropy type of questions regarding message passing, highly non-trivial questions due to the ambiguity of languages. We can ask manipulation type of questions. These type of questions are important, like majority, minority. For example, how many insects are required in order to create a manipulation scenario on a group of humans in just one static setup. We can ask snooker type of questions in manipulation as opposed to a static setup. For example, is butterfly effect observable in manipulation in order to obtain a specified desired effect, or do entropy principles really apply here? Additional problem setup required. Probably, however, is it possible to observe manipulation through fornication only? Is fornication a subset of communication? We expect them not to coincide. Okay. That's about it. Thank you for listening. It's important we as scientists work together on this, and I'm looking forward to hearing about future developments. Thanks for your attention.
Postscriptum. I do have a serious ongoing interest in medical sciences, especially in blocking disease spread. For example, in some regions of the world, pathogenic agents can be as small as mosquitoes, and that aspect did get me curious and baffled at the same time when I was in school. I think we are able to abstract questions like, A. How do these insects communicate between them? Where do they congregate? How exactly do they congregate between them? A question of insect protocol. B. How do they behave? What is it that they do really? What is exactly their style of motion in an environment? Where do they feed from? What is it these insects need in terms of food and reproduction? Questions of interaction, mostly with non-insects. C. How do they communicate with non-insects? Is it right to assume for this particular game only two types of animals of both genders, insects and non-insects? If we are right to assume only these 4 cases, maybe 6 cases if we are to be a little loose here, then that fact is good because it implies good tractability results. Keywords. A. Information dissemination. Rumor spread versus broadcasting. Insects could broadcast if we want to make it interesting, or not. Non-insects communicate and broadcast too, yet I think it would be pretty safe to assume insects have access to these messages. So we can see the problem of blocking disease is already highly non-trivial. B. Wasp colony computation. For example, how far do insects travel? Do they have companions? Do they shuffle with non-insects regularly? C. Predator-prey dichotomy. How is it that they attack? Is it only through chemicals, pheromones, and so on? Or is it right to assume fatal bite capabilities too?